Hi everyone! We've already created several 2D fire effects here, and even one or two 3D ones. This time, we'll return to 2 dimensions and show how to make a slightly different kind of fire using a few layers and a somewhat different technique. So let's get started. And just like last week, we won't apply the effect to an existing image. Instead, we'll generate it entirely on a black background. So I'll create a new scene and set everything up for this kind of shader. Right-clicking the scenes folder, create new scene, and again it would be user interface, and let's call it Wildfire. Okay, and right-click the root node, add child node, and correct, which we'll then set to black color and change the layout. Transform size to Full HD 1920 by 1080. Okay, let's zoom out and scrolling down to the materials section, create new shader material, click it and create a new shader. Type shader, mode canvas item, name wildfire.gd shader, and as usual, I'll put it to the shaders folder. Create and click again to open it in the shader editor. And as always, I'll delete everything from the generated code, so we won't need for our effect, leaving only the fragment function, deleting vertex, deleting white, Ctrl S to save. Okay, so we can begin. You might remember from previous tutorials that at this point, I usually add a uniform parameter called a resolution, which I then use to recalculate the aspect ratio, so the final effect looks the same on any element. This time, however, I won't do that, because with this type of fire, we actually wanted to adapt to the dimensions of its color rect component and make the most of the available space. So instead, I'll start with a parameter called speed, which we'll use to control something like the rising speed of individual flames. Okay, let's put it here, uniform float speed with a hint range and the initial value, let's set to 1. And let's put range to from 0 to, for instance, 10 with a step point 0, 1. Okay, in addition to speed, we'll add 7 more uniform parameters, but I'll get to those while writing the code. For now, let's add a few helper functions, and I'll say a few words about each of them. The first one has a somewhat cryptic name, HSV2RGB. Since it contains plenty of numbers, it'll probably be best if I just paste it in and then describe it. Let's do it here. Pasting. Okay. So, this is a standard formula to convert a color from the HSV format to RGB. So what does it mean? We want to create fire, which is an object made up of colors that lie, so to speak, close to each other, various shades of red, orange, yellow, and their combinations. Moreover, we'll need smooth transitions between these shades to better simulate the changing temperature inside each flame. The standard RGB model isn't very suitable for this because we'd have to calculate the values of all 3 color components in a rather complicated way. However, the HSV model allows us to change just one of them, in this case the hue, while the other components can remain constant. And since the shader works only with the RGB model, we need to convert a color from HSV format to RGB, so we can assign it to the output variable color. If you are interested in the fairly complex topic of colors and color models, I definitely recommend reading the relevant Wikipedia page. I've included a link in the description of this video. Next, we want to add functions for generating pseudo-random values. In other shaders, I usually use variations of Perlin noise, but in this case, something a bit different will be useful. We know that flames often take on a roughly triangular shape, so our base function will follow the same principle. I'll write it out first. Okay, so the next function would be right here, float. So, with the parameter float x, and let's return abs of fract x minus 0.5. Okay, so why did I call this function saw? Let's open Desmos and look at the graph. So where is it? Here. Alright, I often use Desmos in my tutorials. It's one of the best free tools for visualizing mathematical functions. You can find it on the URL desmos.com. Okay, so first I'll create a graph of the fract function, and since Desmos doesn't support it directly, we'll use a formula that produces the same result, which is x minus floor, the integer, floor x. Okay, here it is. This is a typical graph of the fract function, and from 0 to 1. And now I'll subtract 1/2, so we get both positive and negative values. Minus 0.5. Now we can see how it crosses the x-axis. Okay, and finally I apply the absolute value, which gives us the resulting sawtooth shape. Right here, abs. Here it is. Here we go. So now it's probably clear why I chose the name, and we can go back to the Godot editor. Here. Okay, but we'll need something a bit more complex than a simple one-dimensional saw. I'll add a second function called saw3d, which returns a vector 3 composed of combinations of results from the saw function. And to achieve the desired variability, we'll also include nested calls to saw inside it, like this. Let me expand the window, and I'll put it here. Okay. No float, as I said, vector 3. So 3D with the parameter vector 3b for the point in the three-dimensional space, and let's return a vector 3, which consists of these components. So p dot z plus so p dot x, while p dot x is inside this argument, so it's just, as I said, one of these nested calls. And similarly, too many tooltips. So p dot z plus so p dot y. Okay, and the last one, so p dot y plus so p dot x. Okay, and of course semicolon. Very well, that gives us the foundation of our pseudo chaos. As you may know, the next step is usually to use this foundation in a so-called Fractal Brownian motion algorithm. For details, I again refer you to previous tutorials or to the excellent free ebook, The Book of Shaders, whose URL you'll also find in the video description. We'll create a function of this type, but since it will also include flame animation, I'll call it animated noise. However, this function will need the uniform parameters I mentioned at the beginning, so let's add them. The first one is called octaves and represents the number of iterations we'll perform in the loop to compute the final value. Let's add it here, uniform float octaves with a hint range, and I'll start with 5 iterations. Okay, and it goes from 1 to, let's say, 10, and the step is this time 1, of course. All right. The next parameters are directly related to the Fractal Brownian motion algorithm and influence the final appearance of the generated fractal. There are 4 of them, and I'll insert them all at once. Uniform float amp start, which is basically the starting amplitude of the algorithm. It's a hint range and starts at 1.5 and goes from 0 to 5 with a step point 0, 1. Then we need the change of the amplitude after each iteration, so let's call it amp change, and the result is the same, hint range and the initial value. We can also add the frequency change, uniform float frag change with a hint range, and this time it starts at 1.8. Okay, 8 I said, damn it. All right, and again the range is the same from 0 to 5 and 0.01 for the step. And finally I'll add something I called distortion for further distorting of the flame shape. Distortion hint range, and this time it's set to 1.2, and everything else is the same from 0 to 5 with 0.01 step. Great. And now we can write the whole function. Inside it, I'll use the value from saw3d, this one function, as the base value in each iteration, which will then pass through several combinations of the saw function, so the resulting flames are nicely shaped. And of course, we'll adjust the parameter values for subsequent iterations. The result will look like this. Okay, and let's add it after the saw3d function. Right here, float animated noise with parameters vec3 p for the point in the 3-dimensional space, and float noise speed, because as I said, it will be an animated noise, so we need to know the speed of this animation. All right, and now we start with the accumulator called result, start at 0, and at the end of the function we will return this value. And now the implementation. So first, float amp equals amp start. This is necessary because amp start is a uniform parameter, so it cannot be changed, but we need to change the amplitude during the calculation, so that's why I assigned it to a new variable. And now vec3 noise point is p, so this is the input parameter. We can change it, but it will be better readable if we assign it to a new variable as well, and then do some changes in the loop. And now the loop itself, for float I from 0 to the number of octaves I plus plus, I plus plus, and here the curly brackets. Okay, and now first we increase the number of the point by the saw3d function result, which is applied on the noise point. All right, and increased by time times noise speed. So this is the animation. And now we need to do the adjustment of the variables according to how the Fractal Brownian motion algorithm works. So increasing by the frequency change, then we'll increase the amplitude multiplied by amp change, and the final modification is to distortion distortion, multiply the p by the distortion value, and finally let's increase the accumulator. So result is increased by a pretty complex formula. Well, not too complex, but also not too elementary. P dot x plus saw p dot y. So we have 3 nested calls divided by the amp value. Okay, and that should be it. All the preparatory work is done. And now we can move on to the fragment function right here. First, I assign the UV coordinates of the current pixel to the vector UV. Vec2 UV equals UV in capital letters. Okay, as we can see, this time I'm not subtracting 0.5 because although the fire looks centered along the x-axis, it isn't actually symmetrical. So we'll continue working in the 0 to 1 interval. And since we don't want the flames to cover the entire screen, we'll define a mask to limit their influence. Vec2 mask is Vec2 0.5 minus abs uv.x minus 0.5 and uv.y. This is our mask. So it will basically limit the fire to the center of the x-axis with some borders, and then to the y-axis as well. So if we worked with the UV vector in this form, in the following code, the fire would look quite blurry. So I'll add a uniform parameter called scale to eliminate that blur. Let's add it to the uniform parameter section. Uniform float. What was that? Yeah, scale with a hint range, and it starts at 3. And it goes from 0 to 5 again with the step point 0, 1. Okay, and now we can multiply the x coordinate of the UV vector by this parameter. UVx is multiplied by scale. Okay, next, we want the flames to rise slowly upward, so we'll increase the y-coordinate of UV by the chosen speed over time. And because the result would be too fast, we'll divide it by 100. So UV.y is increased by time times speed and times 0.01, which is equivalent to divided by 100. Okay, now we'll need a point in the 3D space representing the current pixel. Yes, even though we are creating a 2D shader, we need a 3-dimensional point. Why is that? Our fractal is actually 3-dimensional, as we can see at this function saw3d, which returns a vector 3 as the result. So we must somehow bring our UV coordinates into the 3rd dimension. The solution is simple. We'll just take a planar slice of the 3D fractal. For that, we'll need the position of this slice, meaning another uniform parameter called slice. Okay, uniform float slice, and the hint range and the initial value can be 1. And let's go from, yeah, why not, again from 0 to 5 with a step point 0, 1. Okay, let's scroll back to the fragment function, and the point, which we'll call P, will look like this. Vec3 P is Vec3 consists of our UV coordinates, the first 2 components, and the slice value as the 3rd one. All right, in the following calculation, we'll work with the mask by multiplying its individual components together. And so we don't have to repeat this multiplication several times over. We'll assign it to a new variable called simply m. So float m is mask x times mask y. Okay, we can now proceed to generating the fire itself. I'll use 2 layers, each with a slightly modified mask and a different zoom level for the resulting effect. It might look something like this. Float fire equals, and I'll just put it to multiple lines to make it better readable, and times 0.5 times animated noise applied on P, and let's say the speed 0.05 plus, and the second layer m times what should be, let's multiply it by m, that could be pretty interesting, times, but lowercase of course, times animated noise again on P, but let's give it some scale, so 0.2 times 0.2, and again the speed 0.05. Okay. And finally, the color. As I said, we'll work with the HSV model and set the hue component according to the value of fire. To place it correctly on the HSV cylinder, we'll multiply it by something and add something else. The remaining components, saturation and value, will stay constant. So it could be like this. Vec3 color is, as I said, HSV to RGB, and now fire multiplied by something like 1.5 and increased by, for example, 0.9, and the saturation I set to 0.6, and the value, the brightness, to 1. Okay, this is our color, and in the end we display the result by assigning the color to the output variable color. So color equals vector 4, color for the first 3 components, and 1 for alpha. Okay, something very interesting is appearing. And it isn't it isn't quite right. We do see some flame over here, but it's fading into a pink background that we definitely don't want. So we need to restrict our color range further. Let's try multiplying the result by the fire value. Okay, so where it is, right here, HSB to RGB with parameters, and as I said, multiplied by fire. Okay, so the pink is gone, but now we can barely see the fire. There is something, but it's not still visible. So what if we multiply by some large constant, like 200 times 200? Okay, so the fire is back, but so is the pink color. Besides that, the fire is larger than we'd like. So we'll add another multiplication by fire. Okay, perfect. And we are done. We have exactly the fire we saw at the beginning of the video, and we can tweak it as needed by changing the values of some parameters. Let's find them here in the inspector, and now, for instance, the speed, so it can be faster growing up, or totally static, just the flames are changing over time. And octaves. Let's try to decrease the number of octaves. So now, when it's set to 1, we can see some hints of the triangular shapes which are generated by the saw function. So that's how our flames are actually built. Okay, or I think the 5 is pretty cool. Or if you change the start amplitude, we can make it brighter or darker. The similar change would happen with the amplitude change parameter or frequency. Now it's more grainy, now it's more blurry, and distortion also affects. Definitely this is a bit surrealistic, I guess, but again, 1.2 is probably the best value. As for scale, we can see how we can see nothing. I must have made some, of course. multiplied and equals a typo. Now it should work. Yeah, and now if I set it to 1, we can see how it would look blurry if I didn't do anything. So multiplying by 3 is definitely nice. And slice. We are scrolling through the 3D fractal and the structure of the flame is changing as well. So this can be used by the script, for instance, to introduce some additional animations or morphing. By the way, in practical use, we'll probably want this kind of fire to render with a transparent background. Now we have a black background. We can achieve that in 2 ways. The first is simpler and consists of setting the alpha channel of the resulting color to the variable M, our mask. So I'll scroll down to the end of the fragment function and right here, instead of 1, I will use M. Let's wait for it. Okay, that's not bad, but it's not ideal either, because the flame itself becomes semi-transparent. We can see it best if we add some image to the background of the scene. So for instance, I can use the one I always use, the fountain JPEG. Let's drag it here. Okay, and of course we need to fix the offset centered and transform position to 0, 0 and the order in the node tree. Now we can see it right here. So we can see there is some fire, but the background image shows through it. In some games this might be precisely what we want, especially if we increase the alpha value, for example by multiplying that by 2. Let's multiply M by 2. Okay. I'd say the solution is definitely worth considering, and we can fine-tune it further by multiplying by other values, 3 or 4. Yeah, I would say it is pretty cool. Okay, and now the second method I've used several times in other effects, and it consists of manually setting a threshold value for transparency. So first, I'll add a uniform parameter to control this threshold. Here, uniform parameters, uniform float, alpha threshold with a hint range, and it starts at 0. It goes from 0 to 1, of course, with a stop point 0, 1. And now we modify the code like this. Here, let's define the average value of the RGB components, AVG equals color R plus color G plus color B divided by 3. Okay. And instead of M times 4, let's do this. If AVG is less or equal alpha threshold, let's use 0, otherwise 1. Okay, and of course, now we see only the fire, but if I change the alpha threshold parameter, okay, let's select correct again, and here it is. Now we can see, we can shape it in various ways. This is not too bad. Okay, and the drawback of this solution is obvious. The flame has sharp edges, so it doesn't look as realistic as in the previous case. But if, on the other hand, we want a stylized fire like this, it might be the right choice for our game. Thank you very much for watching. I think this effect could be useful if, for example, we set an enemy complex on fire in our game or blow up their ammunition depot. The advantage of this shader is that, thanks to the sawtooth-based pseudo-random generator, it isn't demanding on GPU performance. Perhaps we could use multiple instances of it in the same scene and set different slice values, so each fire looks a bit different. Of course, that would need to be tested in a specific example, which I won't do in this video. And of course, I'll add this shader to the Godot shader pack product I linked to in the video description. For now, take care, good luck with your game projects, and I'll see you in the next video.